Alright guys, today in lab we started looking at the pressure at depth in a fluid, and most of you guys kind of figured out that the pressure is due to the weight of the fluid above you. So if you're down in that graduated cylinder, you have pressure from the atmosphere above you, but then also pressure because of the water that is above you as well. And as you get deeper, the pressure should go up. And so if we look at a container of water, the force on the top of the liquid would just be the atmospheric pressure times the surface area of the top of that liquid. And then the force at the very bottom of the container would be the atmospheric pressure times the area, cross-sectional area of the container, plus the weight of all the fluid that's in the container as well. So the force on the bottom then is going to be much bigger than the force on the top. Now, remember that pressure equals force over area. Okay, so if we wanted to find the pressure at the bottom, we would take the force at the bottom and divide it by the area. So if I take force at the bottom equals the atmospheric pressure times the cross-sectional area of the container plus mg, and I'm going to divide each of those terms by area. So we see that these two areas cancel out. But then also the total mass of my fluid is going to be equal to the density of the fluid times its volume, which would also be the density of the fluid times the cross-sectional area of the container times the height of the fluid in the container. So if I take this and plug that in for that mass, then I'm going to see the A's are going to cancel out again. And so the force at the bottom divided by the area then is just going to be the pressure at the bottom. And that is going to equal the atmospheric pressure plus rho times g times h, where rho is the density of the fluid that you're inside. So the equation we have, and the equation you basically should have gotten from your lab today, is that the pressure at any depth is equal to the atmospheric pressure plus rho gh, where rho is the density of the fluid that you're in, g is the acceleration due to gravity, and h is your depth in the fluid. So if you graph that, p versus h, you should get a graph that looks something like this. Okay? This y-intercept then is going to be your atmospheric pressure. And the slope of this line should equal rho g. Now, the density of water is 1,000 kilograms per cubic meter, and g is about 10. So hopefully for your lab today, you got a slope very close to 10,000. If you didn't get that, you might want to go back and check your work. Now this equation will actually work for any two positions within a fluid as well. So let's say I knew the pressure at this point right here, and we'll just call that P naught, and I want to know the pressure at this point, and they are separated by some distance, which we call h. Same equation will work. P will equal P naught plus rho g h. Alright guys, so the first problem I want you guys to try for your homework tonight is that the Titanic was found 2.5 miles below the ocean surface. And so we want to know what is the pressure at that depth. A couple of hints: make sure that you convert your miles to correct units. Also remember this was found in the ocean, so you are dealing with ocean water as your fluid. And make sure you answer the pressure in standard units of newtons per meter squared or pascals. Alright guys, the other thing we're going to talk about tonight is what we call a buoyant force. And a buoyant force is a net upward force exerted on an object that's surrounded by a fluid. So here we have a picture of like a trash can or a big barrel full of water. And inside that barrel full of water, we have a cube, and we're looking at it from the side, so it just looks like a square. Okay? And so what's going to happen is we're going to have pressure pushing down on the top, but we're also going to have pressure pushing up on the bottom. And the pressure on the bottom should be a little bit bigger than the pressure on the top because it's deeper in the fluid. And so the pressure on the bottom is greater than the pressure on the top. We get what we call our net buoyant force. So I'm going to calculate those two pressures. And when I do that, I find that the pressure on the top is 104,000 pascals and the pressure on the bottom is 106,000 pascals. Now I'm going to find the force on the top and the force on the bottom by multiplying by the area of the bottom and top. So when I do that, I find that the force on the top is 4,160 newtons pushing down, and the force on the bottom is 4,240 newtons pushing up. And so what I find is I have a net upward force of 80 newtons, and that is what we call our buoyant force. So our buoyant force in this case ends up being 80 newtons. So there's a net upward force of 80 newtons. Okay, so this leads us to Archimedes' principle. And Archimedes' principle says that the buoyant force on an object is always equal to the weight of the fluid that it displaces. Mathematically, that means that the buoyant force is always going to be equal to the density of the fluid that the object is in times g times the volume of the object that's submerged. So what that means, like in the previous problem, the entire cube was underwater, so the volume submerged would be the entire cube. But if we had a cube floating where half of it was down in the water and half of it was poking out up at the top, like if it was at the surface, then we would only count the part that was down underneath the water line. So let's use this equation to calculate the buoyant force on the cube, and let's make sure we get the same thing. So we multiply the density of water, which is 1,000, times g, which is approximately 10, times the volume of our cube, which would just be 0.2 cubed, and that does in fact come out to 80 newtons. So that shows us that this does give us the same answer. I'm going to give you a little more of a proof of why that works tomorrow in class. It's a little too long to do here. Alright guys, so for your second problem for your homework tonight, we have a setup that we see here where we have some kind of container of water, and we have a wood block that's in the water, and it's being prevented from floating up to the top by a string that's somehow attached to the bottom of the container. So this wood block has a density of 706 kilograms per cubic meter, and its volume is 8 cubic centimeters, and we want to know what is the tension in that string keeping it from floating to the top. Good luck with that, and I'll see you guys in class tomorrow.